Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to General class. This episode is Subelement G9, Question Group A, and I'm your host, Ron Call, KE7CR. This question set particularly asks about feed lines, characteristic impedance and attenuation, standing wave ratio or SWR, and antenna feed point matching. So before we jump into the questions, maybe it would be helpful to go over a little bit about impedance and SWR. And this is one episode where watching the video may help in addition to just listening to the audio. This is a video of SWR. So imagine you have a transmitter putting out a wave on from the left side of the screen towards the right. That would be the green wave. And it does appear that the wave travels down the line. Maximum power is transferred when the impedance of the transmitter matches the impedance of the feed line, and the impedance of the feed line matches the impedance of the antenna. If they don't match, say the antenna does not match the feed line impedance, then it will reflect some of that power back towards the transmitter. That's illustrated by the blue line. Now, when two waves meet, they can enhance each other or subtract from each other. So you'll notice when the blue and the green waves meet, there's a high. For example, in this image, the forward power wave is in the opposite phase of the reflected power wave, and at that point, no wave is transmitting power to the antenna. Whereas at this point, when the forward power wave and the reflected power wave are in the same phase, they're enhancing each other, so you get an additive effect. So the resultant wave is even higher and lower in amplitude. And notice that the red wave stays in position. Those waves seem to oscillate in those same locations. That's called a standing wave. And the standing wave ratio is the ratio of the forward power to the reflected power. If all the power is transferred from the transmitter through the feed line without being reflected, and all of it is sent to the antenna and radiated away, then you don't have any reflected waves, so they don't interfere with the forward waves, and there is no standing wave ratio. That would be the ideal situation. Now, unfortunately, a lot of times there's impedance mismatches. Now remember that impedance is a combination of reactance and resistance. Everything that transfers electricity is going to have some resistance to it. The feed line wire has some resistance, the antenna has some resistance. Now that, in combination with the reactance, now remember reactance is a result of either capacitive reactance or inductive reactance, or both. Any feed line, for example this coax, has a center conductor separated from an outer conductor or shield by a certain space. That's essentially a capacitor. One conductor, a space, a second conductor. So coax has an impedance. This also shows an example of ladder line or window line. It has two parallel conductors separated by a certain distance. That also is a capacitor. And again, any electricity traveling down a wire is going to generate a magnetic field. So both of these generate magnetic fields. The idea with window line is current traveling one direction down one line generates a magnetic field that is canceled by the return current traveling the opposite direction down the other line. And in a coax, current traveling down the center conductor is in the opposite direction of current traveling down the outer conductor or shield, and they should set up opposite magnetic fields and cancel each other. So there should be no reactance in the feed line, but there always is. Every feed line has a characteristic impedance set up by the reactance and the resistance combined. So for example, coax used for HF work typically has a impedance of 50 ohms. Window line, ladder line like this, typically has an impedance of 450 ohms. So with that background about impedance and SWR, let's move into the questions. The first question says, which of the following factors determine the characteristic impedance of a parallel conductor feed line? That's like the one shown here at the bottom, and it's the distance between the centers of the conductors and the radius of the conductors. Neither the length of the line nor the frequency of the signal have anything to do with characteristic impedance. It's just determined by distance between the center conductor and the radius of the conductors. The next question is, what is the relationship between high standing wave ratio, or SWR, and transmission line loss? Now, if you have a high SWR, again, that means that you're losing a lot of power because it's being reflected from the antenna. So high SWR increases loss in a lossy transmission line. The next question, what is the nominal characteristic impedance of window line, transmission line? Again, that's 450 ohms. Next question, what causes reflected power at an antenna's feed point? Reflected power is always caused by a difference between the feed line impedance and the antenna feed point impedance. So when the power is coming from the transmitter through the transmission line, gets to the antenna, if there's a mismatch, it will be reflected back. These illustrations try to illustrate all the power in a wave traveling through the line, nothing being reflected back. So this would be an example of perfect transmission line, where the wave never reflects. This next one illustrates if you have a difference in impedance, the width of the one line represents, say, a different impedance than the thicker line, and when they interface, you're going to get a reflected wave. Some of the power will be transferred to the end of the line, say radiated by the antenna. The rest of the power gets reflected back down the transmission line toward the transmitter. Here's an example with, say, a higher impedance going out and a lower impedance at the antenna. And so again, you get a reflected wave back and a wave going forward. So what causes reflected power at an antenna's feed point? It's a difference between feed line impedance and antenna feed point impedance. The next question asks, how does the attenuation of coaxial cable change with increasing frequency? And the answer is attenuation increases. You're going to have a certain amount of loss or attenuation of your power in a feed line, and that depends on the length of the line, and as frequency increases, the attenuation increases. So what may be a perfectly acceptable length of a line, say for 20 meters or 40 meters for HF work, would be terrible loss at VHF or UHF frequencies. The next question, in what units is RF feed line loss usually expressed? It's expressed as dB or decibels per 100 feet. So for every 100 feet of the line, it tells you how many decibels of loss you're going to have. And remember, 3 dB or negative 3 dB means you've lost half your power. You want to make sure your line loss is rated as low as possible. The next question, what must be done to prevent standing waves on a feed line connected to an antenna? And the answer, the antenna feed point impedance must be matched to the characteristic impedance of the feed line. It's very important that your feed line impedance matches your antenna impedance so that the maximum amount of power will be radiated from the antenna. Next question, if the SWR on an antenna feed line is 5:1, and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line? It's still going to be 5:1. You've just changed the match from the transmitter to the feed line. From the feed line to the antenna is still 5:1. That doesn't change at all. So a better option might be to put a matching network at the feed line to antenna point. In this example, just remember that if the transmitter is matching to the feed line, that doesn't affect the feed line matching to the antenna. Next question, what standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? Now it says resistive load, so there's no reactance component. SWR is written as the amount of forward power compared to how much is radiated from the antenna. So 1:1 means 1 watt of forward power compared to 1 watt of power radiated off the antenna. So if you had 100 watts being transmitted down the feed line and 100 watts radiating off the antenna, you'd have a 1:1 ratio. You could never have a 1:2 ratio. That would mean for every 1 watt sent by the transmitter, 2 watts would be radiated off the antenna. That's not possible. So 1:2 and 1:4 can't happen. SWR is always written as a number compared to 1. And it's either 1 or higher compared to 1. So the standing wave ratio that results from connecting a 50 ohm feed line to a non-reactive, just resistive 200 ohm line would be 4:1. Now to calculate that, you divide the higher impedance by the lower impedance. So it would be 200 ohms divided by 50 ohms. Gives you an answer of 4. So you'd have 4:1 SWR. The next question says, what standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load? Again, you take the higher resistive load, divide it by the lower resistive load number. So in this case, it would be 50 divided by 10, which gives you an SWR of 5 to 1. The last question asks, what is the effect of transmission line loss on SWR measured at the input to the line? The line will lose power. It'll lose forward power. It's lost as heat. The reflected power is also being lost as heat. So you're going to lose both directions. So the answer, higher loss reduces SWR measured at the input to the line. You may measure SWR between the transmitter and the feed line, and it tells you a lower SWR, but you're actually losing more than that. The higher transmission line loss means a larger portion of the reflected power is also absorbed, leading to an artificially lower SWR reading. So your SWR should actually say it's higher than it will show up on your SWR meter when your SWR meter is connected between the transmitter and the input of the feed line. Hopefully that helped you understand impedance matching and SWR a little bit better. And I thank you for joining me on this episode. Look forward to you in the next one. 73, this is KE7CR.